It's my pleasure to introduce Dr. Tony Weathers from our math program, talking about mathematics of infinity.
All right, thanks Dr. Nearing for that introduction, and thank everybody for coming. I would like to add that in addition to this being the last lecture of the 2011-2012 academic year, this is also the last lunchtime talk that will occur at Adams State College. So when you come back in the fall, we'll have new letterhead and such as that. So I want to mention that I used a couple of books from our library as sources for this, and it's really quite remarkable. There's this little book here called Infinity. It was written by this woman at Long Island University back in the 50s. And this is one of the most bizarre math books I've ever come across, because it's, despite her protestations to the contrary, it's really kind of written in almost free verse. And it's all about infinity, and her husband was apparently the chair of the art department there, and he supplied these, interesting illustrations. So if you find today's talk interesting, I would encourage you to go and get this book. It's really quite readable, and that's why she did it the way she did it. And it's kind of strange. The other book that I used as a resource, and another book that I recommend, is this one. It's by the Eli Mayor. It's called To Infinity and Beyond. So before it was Buzz Lightyear's catchphrase, it was the title of this book, and it's got a really interesting picture on the front, and I don't know if you can see that. So I got a better version of it for you here. Some of you might be fans of M.C. Escher, and you might recognize this. This is a print done by M.C. Escher in 1958. He called it Sphere Spirals, and I guess somehow the author of this book thought that it captured the notion of infinity. And this ought to look somewhat vaguely familiar, even if you're not an M.C. Escher fan. Does anybody recognize this? Well, perhaps if I show you a different rendition of it, right out next to our very own business building is this sculpture, which I'm guessing was inspired by the M.C. Escher print. Now, what would cause me to think that this was inspired by it? Well, let's see, did anybody recognize this? Has anybody ever walked over and looked at this thing up close? No? Well, as all good sculptures do, it has a name. Guess what the name of this sculpture is? Infinity. Okay? And so right here on the grounds of our very own Adams State, soon-to-be university, is a representation of the Escher sphere spirals. And so with a name like that, you pretty much guess that he had to be thinking about the M.C. Escher. But anyway, so there you go. A neat little sculpture right here on the grounds. So, well, what are we going to talk about today? We're going to talk about infinity. And so infinity is something that people have been kicking around for a long time. One of the earliest thinkers who addressed the notion of infinity was none other than Aristotle. And Aristotle had an interesting take on it. He accepted the idea of what he called potential infinity, but he rejected an actual infinity. Now, what did he mean by that? Well, he accepted the idea that there were some things that just kept going. Like, for instance, you talk about natural numbers, the counting numbers, some people call them 1, 2, 3, 4. And Aristotle was savvy enough to realize that there is no largest natural number. No matter what natural number you go out to, you can always add 1 and get another natural number that's larger than that. And so in that sense, he said, yes, there is such a thing as a potential for infinity, but that there is no such thing as an actual infinity, an infinity that could be conceptualized as a whole. And he was not alone in this. And in fact, he was not even, it was not just the fact that, wait a minute, I lost my train of thought there. Everybody in here probably has heard of Carl Friedrich Gauss. There's a biography of Gauss called Titan of Science. He had his hand in lots of things, and he himself rejected the notion of an actual infinity. He in fact said, and I have a nice quotation here from Gauss, he was writing to one of his colleagues who was doing some things very similar to what we're going to be doing in a few minutes. And he said, "I must protest most vehemently against the use of the infinite as something consummated, as this is never permitted in mathematics." Okay? So he was right along with Aristotle with this idea that infinity isn't something that you can reach or that you can conceive in a totality. It's this notion of endlessness, that things keep going. I often tell my students that you ought to think of infinity really more as of a verb than as a noun, because it doesn't really say that there is this thing that is infinite. It says that you can just keep going and keep going. And Aristotle would have been very much at home with that, rejecting the notion of an infinite object that could be, well, as Gauss would put it, consummated in its entirety. Okay. Well, why is this important? Well, I'm going to try to go through some derivations of some ideas with sets to show you why you need to be able to talk about infinite sets. Right? And so let's talk about how comparing two sets of numbers. All right? Now let's imagine you have two finite sets. You have a set that contains 1, 2, 3, 4, 5, and the set A, B, C, D, E. And you're asked the question, are these sets equivalent? Do they have the same number of elements? Well, it's very easy to see in the case of finite sets that yes, they do have the same number of elements. And how do you see that? You just count them, right? You go to the set on the left and you count it. 5. Go to the set on the right and you count them. 5. They have the same number of elements. Okay, so they must be the same size. They must have the same number of elements. They must be equivalent, okay? However, maybe I should switch to this thing if it'll work. When it gets to infinite sets, things get a little bit squirrely. Because how would you decide whether these sets were equivalent? Well, you start off by counting all the things in the set on the left. Okay, go. Now, when you're done with that, you'll never be done with that. I mean, you can't apply the same sort of strategy. You can't just say, let's count the things in the set on the left and let's count the things in the set on the right, and if we get the same number, then they must be equivalent. Okay? So there's got to be a better way. And one of the most prominent mathematician who tackled this problem was this guy, Cantor, Georg Cantor. You see, he lived in the latter part of the 19th century there. And he was, well, let's see, he was born in Russia to a Danish father and Russian mother, and then moved to Germany at the age of 11 and spent the rest of his life working in Germany. And he realized that we got to have some way to compare two infinite sets, other than just saying, let's count all the ones in this set and let's count all the ones in that set. And he stumbled across an idea that is startling in its simplicity. Okay? He said, two sets are equivalent if and only if there is a one-to-one correspondence between them. Okay? And a one-to-one correspondence means that you can match up every element of this set with one and only one element in the other set, and you can do that all the way down. And it's really remarkable to me how long it took somebody to come up with this idea. Because you've probably used the idea of one-to-one correspondence to make equivalent sets. Children use the idea of one-to-one correspondence to make equivalent sets. I mean, you give two kids play, you give them a bag of M&Ms and say, here, divide these up. What do? They dump them out, they count them, and no, they don't. What do? One for you, one for me. One for you, one for me. I mean, that's the notion of a one-to-one correspondence. And it's something very natural. It's something that kids can do. In fact, if you have preschoolers, does anybody have small children in here? Hey, there one. Have you ever watched the show Miffy? Miffy is a show on Nick Jr. that follows the adventures of Miffy, the cute little bunny on the left. Okay? And you can go online and play games. They play games during the show, and one of the games is called The Same Game. And it's a way to introduce toddlers to the notion of two sets being the same size. Do Miffy and Poppy Pig have the same number of flowers? Well, no, they don't. And you can see that very readily because you see that the one-to-one correspondence breaks down here. You line them up, there's a one-to-one correspondence. Whoops, poor Poppy, he's out of, he doesn't have the same, okay? So the point I'm trying to make here is that this is really a very basic, very simple notion, the notion of a one-to-one correspondence, but it has some surprising ramifications. So, back to our friend Cantor. So, when he set out to start comparing infinite sets, he realized he had to have some kind of baseline for comparison. So what he decided to do was to use the natural numbers. Okay, so he says, I'm going to start comparing sets to the natural numbers. Now, what are the natural numbers? Well, again, some people call them the counting numbers, and it's just the numbers 1, 2, 3, 4, 5, 6. And so he says, well, I want to say how many elements are in this set so that I can compare other sets to it and say that they have the same number of elements. Well, it's got more than 5 elements. It's got more than 10 elements. So, well, he decided he was going to have to invent a new number, what he called a transfinite number. Okay? And the transfinite number, he decided to use the first letter of the Hebrew alphabet. So this is the Hebrew letter Aleph. Okay, how about that? Aleph sub-zero, which mathematicians typically refer to as Aleph naught. The little bars around here is simply saying that we're counting the number of elements in the set, in the natural numbers, and he said we're going to set that equal to this, what he called a transfinite number, Aleph naught. Okay, so the cardinality of the natural numbers is defined to be this Aleph naught. Between 1879 and 1884, he wrote a series of 6 papers which established the foundations of what mathematicians now call axiomatic set theory. He called it Mingenlehre, I think is the German word for it. Okay? And then in 1884, well, I'll talk about what happened in 1884 a little bit later. So now, notice that this way of comparing sets works just the way you would expect for finite sets. Okay, so you take your 2 finite sets, and if they are indeed equivalent, then you should be able to pair every element of the first set up with exactly one element of the second set. And you can do this all the way down the line. And it works just fine for finite sets and delivers the same results that you would get if you just counted them and then compared the numbers. All right? But the nice thing about it is it works even for infinite sets. Okay, so he said, look, you take your natural numbers there, 1 through on, etc., and then look at just, say, the even natural numbers. Okay, can you make a one-to-one correspondence between the set of natural numbers and the set of even natural numbers? Why, yes, you can. And you could even write down a nice formula for this if you wanted to call the elements of the first set n. Okay, then the elements of the next set are 2n, right? And so you have this formula that tells you if you give me any element in that first set, I can tell you what element in the second set is paired up to it, right? And vice versa. So the conclusion is that these 2 sets are equivalent. And what does that mean? That means that they have the same number of elements, right? Which leads to a somewhat, perhaps mildly surprising result, which is that there are just as many even natural numbers as there are natural numbers. Okay? Despite the fact that one set looks twice as big as the other. No, it's not so. There are just as many even ones as there are regular ones. A nice corollary to this, you can imagine doing this with the odd ones as well. And so there are just as many odd natural numbers as there are natural numbers. Well, this leads to an interesting result with arithmetic of transfinite numbers. Because, I mean, you can clearly see that if I take all the odd natural numbers, okay, here on the left, and I take all the even natural numbers here, if I union is just a fancy way of saying take the 2 sets and dump them in together, what do you get? You get all of the natural numbers. And so you have 2 sets that are the same size as the natural numbers, yet when you put them together, you get another set that's the same size. Okay? And so you wind up with a curious property like this. Okay? And of course, this is, I mean, Aleph naught plus Aleph naught is Aleph naught. Okay? Which is not close to the most surprising result that you can get with transfinite arithmetic. Okay? All right. So then Cantor continued to explore this notion of sets that were equivalent to the natural numbers. All right, so if you're in a math class and you're learning about numbers, you learn about natural numbers, well then you learn about a new set, a bigger set, the integers. Okay, so let's talk about the integers. What are the integers? Well, the integers are formed by taking the natural numbers, okay, stick 0 in there, and then you throw in a bunch of negatives. And Cantor wanted to see if he could come up with a way to show that the set of integers was equivalent to the set of natural numbers. Right? Now, what does it mean to show the 2 sets are equivalent? It means there's a one-to-one correspondence between them. Okay? And so what I want to convince you of next is when you talk about making a one-to-one correspondence between the natural numbers in any set, that's really just a fancy way of saying that you can list them, right? Because what does it mean to be put in one-to-one correspondence with the natural numbers? It means that there is something that corresponds to 1. We'll call that one first. There's something that corresponds to 2, so we'll call that one second. Something corresponds to 3, so we'll call that third. So when a mathematician says, oh, it can be placed in one-to-one correspondence with the natural numbers, what he really means is, well, we can list them. But we can list them in such a way that we don't miss any of them, all right? All right, so here we go. So now we've got the integers. The integers, as I mentioned, it's got 1, 2, 3, all right? It's got your natural numbers there. You throw 0 in, you throw in all the negatives, and now we have a set that, well, is this equivalent to the natural numbers or not? I mean, no, I see some heads shaking. Why not? What's wrong with this? What's different? Say what? Okay, you've got negative numbers. I mean, it looks like what I generally get students to say in like our liberal arts math classes, they'll say something like, well, this one goes to infinity in 2 directions, right? It's not just going off to infinity that way, it's going off to infinity that way. So clearly, beware when a mathematician says clearly. Clearly this set is larger. Well, that wouldn't make any sense, would it? And in fact, it's not. Okay? So how would you make a one-to-one correspondence between the integers and the natural numbers? Well, you cannot simply say, all right, we'll let this correspond to 1, and then 2, 3, 4, 5, because you're going to miss all the ones down there. So maybe you got to turn it around and go the other way and say, well, this is 1, and then 2, 3, 4, 5. No, because then you're going to miss them all this way. So how do we resolve this dilemma? Well, we break it. Well, here's what we do. So we take the integers, whoop, come on. Take the integers and break it into 2 sets. So we'll take everything from 0 on up into one set, and everything from -1, -2 on down, okay, make it into 2 sets. And now what we do is, well, it's just like playing cards. You just shuffle them back together, okay? And so you shuffle them back together like this, okay? Now, can you see that this is still going to give me all of the integers, right? Still got all the positive, positive, these are the ones, all the negative ones. So you still have all of the integers. And you can write down a formula for a one-to-one correspondence from the natural numbers to this set. But you don't really have to do that because you can see that this is a list, right? This would correspond to 1, 2, 3, 4, 5, 6, 7. And there you go. We have all the integers in a nice list. So we have a one-to-one correspondence between the integers. So of course this set isn't any bigger. I mean, it's infinity, duh, right? Let's see, is Dana here? Did Dana? We had an art student some years ago who took the liberal arts math class, Bill Birch. I don't know if any of you remember Bill Birch. But when we were discussing this in the liberal arts math class, that was his phrase. Well, of course it's not bigger. It's infinity, duh. And so thanks, Bill, if you're watching. So what do we conclude from this? That the integers are the same size as the natural numbers. Despite the fact that it looked like it could be bigger, well, of course it can't be bigger. It's infinity, duh. Sorry, I just like that. Good old Bill. All right, so we work our way up through progression, all right? So we started with the natural numbers, we developed the integers. Well, of course, not all numbers are integers. There are certain things that are, well, they're fractions, right? Mathematicians call these things rational numbers. And so let's talk about the rational numbers. Okay, so here's a fairly rigorous definition. The rational numbers, it's represented by Q because rational doesn't have a Q in it. It's actually from quotient. Which, by the way, you might wonder why Z is the symbol for the integers. It's from the German word for numbers, Zahlen, okay? So the rational numbers are formed by taking any 2 integers, as long as the one on the bottom isn't 0, and making a fraction. So it's all the fractions, right? Now, the integers, they look a lot like the natural numbers. Once you do the reshuffling, you spit them out there, and you have the 0, 1, -1, 2, -2. The rational numbers, they look completely different than the integers do. In particular, they have a property that I'll come back to in a little while called density. which is to say, this is one way of saying it, that between any two rational numbers, you can always get another rational number. I mean, it doesn't really matter how close they are, 1/3 and 1/2. Okay, those are two rational numbers. There is another rational number between them, and how do you get it? Well, the easy way is you just add those two, divide by 2, right? You take the average of them, okay? But what this means is that no rational number has an immediate successor in the rational numbers. Okay, if you're standing on the integers and you're at 5, you say, what's the next integer? 6. Okay, and so it very easily lends itself to this one-to-one correspondence with the natural numbers. They're already listed. But you can't do that with rational numbers. So you go out to 1/2. What's the next rational number? There is no next rational number. So you can't just rely on the natural order of the rational numbers to try to make some kind of list. You just can't do it. So maybe we finally found another set that's bigger than the natural numbers. Maybe we finally found a set that cannot be placed in one-to-one correspondence with the natural numbers. Well, no, we haven't. Okay? And so what Cantor realized, he came up with a way to show that you can list all of the rational numbers. Now, it's a rather intriguing argument, and so, wow. Okay, so my graphic here is, I hope you can all tell what these are. So what I've done here is I have listed out just the positive rational numbers, okay? So forget about 0, forget about the negative ones. Let's just look at the positive ones for a moment. And what I've done here is I've listed in the first row all the fractions that have a denominator equal to 1, okay? All the fractions that have denominator equal to 2, equal to 3, equal to 4, etc., okay? Now, it's pretty simple to see that each one of these rows must be equivalent to the set of natural numbers, okay? But how many rows do we have? Well, we've also got a number of rows that corresponds to the natural numbers. So we've got infinitely many infinite sets here. It's not like the integers where we broke it into 2 infinite sets and then shuffled them back together. Now we've got infinitely many infinite sets. And so how are we going to do this? Well, again, we can't just run a list down here and say this is the first one, second one, third one, fourth, because our list will never stop and get us to the second row. And so you think, well, maybe we could do it by columns. All right, so maybe this is the first one, and this is the second one, and this is, well, again, you have that problem that you'll never get finished counting that column. And so what Cantor realized was that he could do this by blending the two approaches. So what he did was, he says, okay, we're going to make this our first number in our list. And then we're going to go over and we're going to make this the second number in our list. Now again, we know we can't just keep going off to the right because we'll never finish. So he says, now we're going to go down the diagonal here. Okay, and the diagonal, so we go down here and we pick up 1/2. Okay, so that thing's not working very well. Then what? Then we scoot down here, we pick up 1/3. And at this point, the pattern starts becoming a little more clear. As soon as we get down here, what we're going to do is we're going to travel back up along this diagonal to get to the first row, move over, and come back down. But we got to be careful, because remember, this is supposed to be a one-to-one correspondence, and you'll notice that if I start traveling back up along this diagonal, the first number I encounter is 2/2. Well, that's actually equal to 1/1, and that would blow up my one-to-one correspondence. So what I'm going to do is I'm going to skip that. And so the general rule here is we're going to work our way through this array in this diagonal manner, but we're going to skip any fraction that's not in lowest terms. Okay? So 2/2 is not in lowest terms, so I'm going to skip it. And I'm going to go back up to the first row and pick up 3. Okay, so now I've got those numbers, move over, get 4, and then work our way back down this diagonal. And you can see that another way to describe this is you can see that all the fractions on this diagonal have a numerator and denominator that add up to 5. Okay, so that's another way you can describe this procedure, is by looking at the fractions listed in terms of what the sum of the numerator and denominator are. And so you work your way through here like this, skip down to 1/5. Now notice that all of these, 2/4, that's not in lowest terms, 3/3, that's not, 4/2, that's not. So then we skip all the way back up, but we eventually will work our way through this entire array of rational numbers. And so you will have a list. It's kind of hard to come up with a formula for saying exactly what the nth number in this list is because of the peculiar way we've worked through it. But you'll wind up with a list of all positive rational numbers. And so there you go. There's a one-to-one correspondence between the positive rational numbers and the natural numbers. Well, how do we extend this to show that the rational numbers in their totality are equivalent to the natural numbers? Well, throw in 0. That's just one more number. Just everybody scoots down one. Okay? Then you can do the same thing with the negative rational numbers, and then, again, you could sort of shuffle them together. So what this shows is that the rational numbers are the same size as the natural numbers. Okay? And this is a mildly surprising result, I would hope. Because, again, and it comes down to this density property of the rational numbers. I mean, the integers don't have that. I mean, you have two integers, any two integers are at least one apart, right? But rational numbers, they're all over the place. They're dense, okay? Now, if you think about that array for a moment, remember those rows, I said we can imagine each row quite easily as being equivalent to the natural numbers. And you have one row for each natural number. And so you can come up with another kind of surprising sort of transfinite arithmetic that says not only can I add 2 of these aleph naughts together, I can add all of them together. I can add aleph naught, aleph naught, aleph naught. I can keep doing this all day long, and I'm still never going to get anything bigger than aleph naught. And why not, Bill? Because it's infinity, duh. Okay. All right. Okay, so let's see. What's next? Well, we talked about the irrational numbers, or talked about the rational numbers. Of course, you know that not all numbers can be represented as fractions. At least I hope everyone in here knows that. I mean, there's some very famous examples: square root of 2, pi, e, Euler's number. So there are lots of numbers that cannot be written as fractions. These are called the irrational numbers. And when you take the irrational numbers and dump them together with the rationals, then you have what we call the real numbers. Now, surprisingly, coming up with a rigorous definition of irrational numbers is quite hard. Because what are they? Well, they're the numbers that aren't fractions. How do you know there are such things? I mean, what does one look like? How could you write it down? Well, actually, so you've probably encountered these before, irrational numbers, and you were probably told at some point in your life that you know that all numbers can be represented by decimals. Rational numbers have a very nice decimal expansion. If you write out the decimal for 1/2, what do you get? 0.5. You write out the decimal for 1/3, what do you get? 0.33333333. So you see an example where a rational number has a decimal expansion that terminates, and you have one where a rational number whose decimal expansion doesn't terminate, but it does repeat. And it turns out that all rational numbers have decimal expansions that do one of those two things. They either terminate or they repeat. And so then you can give what I like to call the grade school definition of an irrational, which is it's a decimal number that does not terminate or repeat. Okay? So, let's see. And this is what I just said there. So when you take the rationals, you put them together with the irrationals, now you've got the real numbers. Okay? And so, what about these irrationals? Well, I mentioned to you that the irrationals are kind of hard to get a handle on. You might be surprised that it wasn't until 1858, which is kind of recent in the history of mathematics. It wasn't really until 1858 that this guy, Dedekind, came up with a way to rigorously, in a set theoretic way, define the irrational numbers. And, well, of course, he used the rational numbers to do it, which is fine, but that's kind of surprising, I think. As I said, that's fairly recent in mathematical history for people to finally get around to identifying or rigorously defining the irrational numbers. And so we put the irrationals together with the rational numbers. And now, what about this? Are the real numbers equivalent to the natural numbers? Well, for purposes of of simplicity, what I'm going to do is I'm only going to look at the real numbers between 0 and 1, okay? So sort of like when we did with the, if we can do it with the real numbers between 0 and 1, then we can certainly do it with all real numbers, okay? It would be a short step from there. And so here's what I've got. Let's imagine that we can list all the real numbers between 0 and 1. In other words, let's imagine that there is a one-to-one correspondence between the natural numbers and the real numbers between 0 and 1. Now, what does that mean? Well, I've already told you. It means that we could list them out. So let's imagine that I have a list. So here's a list of real numbers between 0 and 1. And let's imagine that I say to you, this is all of the real numbers between 0 and 1. So you see I've got a first one and a second one and a third one and a fourth one. Now, I'm not pretending that I have some sort of formula for this, okay? This is just, this would be the beginning of the list. The list, as you can see, keeps going on and on. And you see in here, well, here's an obvious rational number, right? That's still a real number, right? Because the reals, it's the rationals and the irrationals, okay? And you get your rational number like 1/3, okay? Here, surprisingly, this actually turns out to be an irrational number. You can prove that, okay? It doesn't repeat, okay? Just because it has a pattern doesn't mean that it repeats. And so there you go. We have this list of all the real numbers between 0 and 1. All right? Now what? Well, I'm going to pick out a real number between 0 and 1. And I'm going to construct it. And I'm going to construct it in a very special way. So I'm going to start with 0 point, because of course the decimal expansion for any real number between 0 and 1 is 0 point something. And I'm going to construct the number this way. I'm going to look at that first number there. That first number, I'm going to look at the first decimal place. And I see that that's a 1. So what am I going to do? I'm going to pick something that's not 1. Okay? And, oh, I don't know, how about 2? Okay? So then I move to the second one. I go to the second number, and I look at its second digit, okay, the second decimal place of the second number. I see that that's a 3, so I'm going to pick something that's not 3. 6, maybe. Okay? This technique has become known as Cantor's diagonalization technique for obvious reasons. And what we're going to do is we're just going to proceed through here. So I'm constructing this number up above by looking at the numbers below. So I go to the third number in the list. I look at its third decimal place. I see that that's a 0. So what do? I pick something that's not 0. Okay, how about 1? And so on. So that one, the fourth decimal place of the fourth number in the list is a 2. So I pick something that's not 2. 3. That's not 2. I go to the fifth decimal place in the fifth number. I see what that is. I pick something different. And so on. And so on. And so on. Okay? And so what have I done? I've constructed a number that there's no doubt that this number is a real number between 0 and 1, right? Because the decimal starts with 0 point something, 261379631, blah, blah, blah. And now here's the question. Where in my list is this number I just constructed? It's not the first number in the list, obviously. It's not the second or third, or it's not any of the first 9 numbers. How do I know it's not? It might be the 10th number, though. It might be the 10th number in my list, might it? Mightn't it? Could it be? Well, now wait a minute. Think about how we constructed this. I specifically chose the number or the digit for the fifth decimal place by looking at the fifth decimal place of the fifth number. And so even if I couldn't see this fifth number, I know that my number isn't this one because it differs in the fifth decimal place. Right? And same thing with this guy. Even if I couldn't see the 7th digit, if this were blurry like that slide before, okay, and I couldn't actually see this number, I know that my number I've constructed cannot be equal to this one because I specifically chose something different in the 7th decimal place. So even though I can't see the 10th number in this list, I know that my number, at the very least, is different in the 10th decimal place. Okay? So, well, maybe it's the 100th number in the list. No, it can't be because I specifically picked my 100th decimal place to be different from the 100th decimal place of the 100th number. And so what's the conclusion here? The conclusion that we're forced to, this number's not in the list. Well, now, wait a minute. You said that this list contained all the real numbers between 0 and 1. Oh, well, I must have missed one. But what it really means is that no list of real numbers between 0 and 1 could possibly contain all of those real numbers. Any list you give me, doesn't matter what sort of formula you use to create that list, I can always generate another number between 0 and 1 that's not in that list. So that tells us a set of real numbers is actually bigger. It's a bigger infinity. It's an infinity that's, well, for lack of better terms, it's more infinite than the others. And it's not just bigger. I mean, this is a completely different kind of infinity. This is so huge. This set is so big, you can't even list them all. All right? And go back to the rational numbers. You say, well, maybe I need 2 lists. It doesn't matter. You could have infinitely many lists, right? You could have one list for each natural number, each of which has as many numbers in it as the natural numbers. And, well, that looks just like the rational numbers now. It doesn't matter. You cannot do it. The natural numbers are simply smaller than the real numbers. A set of real numbers is a larger infinity. Okay. Whoa. Now you see why we have to subscript the cardinality of the natural numbers with aleph naught. Because this opens the door to a whole slew of transfinite numbers. In fact, there's an infinity that's even bigger than the infinity of the real numbers. And it's called aleph 2. There's one even bigger than that. At each stage, these things, again, this isn't a bigger infinity like taking the natural numbers and adding 1. You'll hear kids that, oh, I hate you a million times. I hate you infinity. I hate you infinity plus 1. Hey, bad news, kid. Infinity plus 1 is still infinity. Okay? This is a completely different kind. I mean, these infinities are big. They're weird. This is a whole different class of infinity. And then aleph 2, aleph 3, that's even worse. Now here's an interesting question, though. What we've just shown, what this Cantor's diagonalization proof shows, is that the set of real numbers is more numerous than the set of natural numbers. Okay? And he was able to show, under certain assumptions, certain very technical assumptions, that once you have this aleph naught, there's an aleph 1 and an aleph 2 and an aleph 3. So what we know is that the real numbers are at least as big as aleph 1. But maybe it's bigger. Okay? In other words, could it be that there's a set that's somewhere between there? So is the real numbers, does the cardinality of the real numbers, does that correspond to this aleph 1? Or is it maybe aleph 2 or aleph 3? Maybe there's some more sets in between there that we haven't found. So is there a set that's bigger than the natural numbers, yet smaller than the real numbers? More infinite than one, but less infinite than the other? Well, Cantor thought about this and decided, he said no. Okay? He said this has become known as the continuum hypothesis. And Cantor was quite sure at the time that no, there is no set between those two. The next transfinite number, aleph 1, corresponds to the cardinality of the real numbers. So that's really what the continuum hypothesis says, that the cardinality of the real numbers is this number, aleph 1. And at one point, he was this close to publishing a proof of the continuum hypothesis when he realized that he'd made an error in his proof. So he retracted it and then found a way to disprove. Oh, hey, I was wrong. So he came up with a proof that the continuum hypothesis was false, and I don't think he got quite that close before he realized, no, wait a minute, that's not right either. And so this became a rather interesting question for mathematicians. Let's see, when was the Hilbert? Hilbert's, was that 1900, 1909, sometime in the early 1900s, David Hilbert, celebrated mathematician, addressed a large international group of mathematicians and put forth a list of the most important unanswered questions that we need to be working on in the next century. and I forget how many there were, 20-some questions on that list. And number one was the continuum hypothesis. Okay, he thought that that was so important that he wanted to direct everybody's attention to it. We need to figure out if this continuum hypothesis is true or if it's false. Okay? And so, well, spurred on to action, mathematicians attacked it with vigor. And they tried to prove it, tried to prove it, tried to prove it. And so, well, couldn't prove it, couldn't prove it, couldn't prove it. So what do you do as a mathematician when you're trying to prove something and you can't do it? Well, you might try what we like to call a contradiction proof. You assume that it's false and see if you can get some kind of contradiction, okay? And so in 1940, and you'll love the twist here, in 1940, a guy named Kurt Gödel proved that you couldn't disprove it, okay? So, well, if you can't disprove it, then the obvious conclusion, well, okay, yeah. Any takers? The obvious conclusion is that it must be true and you can prove it. Unfortunately, in 1963, it was proved that you couldn't prove it either. Okay, so chew on that for a moment. They proved that it couldn't be proved or disproved. All right. Now I'm taking some liberties with the terminology. Actually, what was shown was that the continuum hypothesis was independent of all the other axioms of mathematics. If you assume that it's true, then you don't get any kind of contradiction. You go off and you do your happy little mathematics. If you assume it's false, you still don't get any contradictions, and you can still do mathematics. Now, you'll do a different kind of mathematics than you will if you assume that it's true versus assuming it's false. But it can't be proved or disproved. And so now we know why Cantor was having such trouble. I should mention that, as I said, between 1879 and 1884, Cantor published a series of 6 papers in which he laid out many of these ideas. At one point, he wrote in a letter to Dedekind, by the way, about some of his results, "I see it, but I don't believe it." And it's his own proof that he's talking about here. I see it, but I don't believe it. And then in 1884, he suffered the first bout of mental illness. And it's really not funny because he got into some squabbles with some of his colleagues, and especially a guy named Leopold Kronecker, because his ideas were not well received. And I mean that in a big way. What I'd like to do is I'm going to read you some quotations from some of his contemporaries and later folks about this business. So if that made you squirm a little, seeing, what do you mean one infinity is bigger than another? Well, here are some professional mathematicians weighing in on the subject. Poincaré, which some of you may have heard that name, was quoted as saying, "There is no actual infinity. Cantorians forgot that and fell into contradictions. Later generations will regard set theory as a disease from which one has recovered." Okay? Brouwer, which mathematicians, you may have heard of the Brouwer fixed point theorem. He's a famous topologist. He wrote that Cantor's theory as a whole is a pathological incident in the history of mathematics from which future generations will be horrified. Okay? And then Kronecker, who was formerly, as I say, a good friend of Cantor's, said, "I don't know what predominates in Cantor's theory, philosophy or theology, but I am sure that there is no mathematics there." Okay? Even Ludwig Wittgenstein, the famous philosopher, said Cantor's argument has no deductive content at all. Hermann Weyl, a famous mathematician physicist, said that the axiomatic set theory is a house built on sand. So, I mean, even supposedly smart guys, mathematicians, contemporaries of his, rejected these ideas out of hand. And it was especially the conflict with Kronecker that according to many sources, led Cantor into depression. He was in and out of sanitarium for the rest of his life, and in fact died in a sanitarium. So don't go thinking too hard about this stuff. Now, I could stand up here all day, if I wanted, and tell you weird and puzzling consequences of this, but so I thought I'd pick a couple just to show you some more peculiar results here. So let's talk about a finite set for a moment. Suppose, let's imagine a deck of cards. Imagine I were to tell you that I have a deck of cards, and this deck of cards is arranged in the following manner. Between any two red cards, there's a black card. Between any two black cards, there's a red card. Okay? Well, you think about that for a few minutes, and what you realize is that that would imply that the deck must be alternating. Red, black, red, black, red, black, red, black, red, black. Okay? And since it's a deck of cards, and there's an even number of them, what you could say is, well, that there are the same number of red cards as there are black cards, right? If you have any finite set with this property, that between any two of one, there's the other, and between any two of these, there's that one, then, well, okay, at most there's one more of one than the other, right? If it's an odd number, the ones on both ends might be red, okay? Well, why is this important? Well, think about what happens with an infinite set. Now, I told you that the rational numbers were dense. Well, the irrational numbers are dense as well. And that only stands to reason. There's more irrationals than there are rationals, right? Okay. How do we know that? Well, because you can do Cantor's diagonalization proof, by the way, just with the irrationals, and it still works. Okay. So, but it's even worse than that. Between any two rationals, there's an irrational, and between any two irrationals, there is a rational. Now, wait a minute. You just said that the set of rational numbers is tiny compared to the set of irrationals, right? One of them is this aleph naught. The other one is this other type of infinity that's so huge, I mean, you can't even line them up. And yet, in a certain sense, they're shuffled together. Between any two rationals, you can always find an irrational. Between any two irrationals, you can always find another rational number. How can there be more of one than there are the other? It's infinity. Duh. Duh. Okay. Another interesting consequence of the density of the rational numbers, something you might not have thought about before. Okay. We said between any two rational numbers, and when we say something like that as a mathematician, we mean two different rational numbers, there's got to be another rational number. Okay, so here we have the rational number 0.9999999, okay, and the rational number 1. What number lies between those two rational numbers?
Lots more nines.
Well, but the 9s go on to infinity. So what number lies between them? Well, the inescapable conclusion, there isn't one. So what does that mean? That means that 0.99999 repeating is actually equal to 1. I mean, equal. It is the same number. It's not the last number before you get to 1, because remember, we said that rational numbers don't have any immediate successors or any immediate predecessors. There is no last number before 1. The number 0.999999 is exactly equal to 1. Believe it. Okay. Any questions?